use metal as conductors there. We will be focusing on these two different types of bound in this particular learning objective, and then later on in this chapter and the next, we are going to take a closer look at the covalent bond. How are the atoms sharing their electrons with one another? Okay, and so talking about two different types of chemical bond there, ionic and covalent. These are actually two extreme situations. And now yesterday we were talking about the periodic trend, and you see some of the properties there recurring itself repeatedly when you go from left to right to the periodic table. Now you see metals on the left, non-metals on the right. So somewhere in between you see the transition metal. And the same way in terms of the chemical bonding there, ionic bound is an extreme situation. Covalent bound is another extreme situation. Okay, so pretty much most of the chemical bonds are somewhere in between. And when you have metal and non-metal, typical, you end up with ionic bound. When you have non-metal and non-metal, well, they are going to share the electrons. But each one has we introduced that concept yesterday, electronegativity. Remember that slide that I gave you here with a huge red arrow pointing from the lower left corner of the periodic table up to the upper right corner of the periodic table. Electronegativity. Electronegativity is the measurement of the ability of atoms in a molecule to attract electrons toward itself. So if you have non-metal reacting with one another, when they're sharing electrons, each different atom will have a different ability to attract electrons toward itself. So in a sense, you may not have an equal sharing between the two non-metal elements there. Now, how do you differentiate between an ionic bound and unequal sharing? Well, the ionic bound is transitioning into a covalent bound when you move from left to right, when the elements that you use to form the molecule, or to form the compound, I should say, and is getting closer and closer to one another on the right side of the periodic table. So these are two extreme situations, and then covalent bonding in the case of water, there you have hydrogen, you have oxygen. Now hydrogen is group 1A, oxygen group 6A. So you know oxygen will have a much stronger ability to attract electrons toward itself. As a result, when you have a higher electron density, by attracting more electrons toward yourself, you get a bare negative charge. Now, hydrogen electrons are being taken not completely away. It's shared with oxygen, but the electrons are further away from hydrogen atoms. So in a sense, hydrogen atom would bear, in this case, a partial positive charge. Oxygen will bear a partial negative charge. And still, the overall molecule is charge neutral. The net charge equals to 0. So what we're trying to do here is that we are trying to understand how the electrons are being shared, in particular within the covalent bound molecule. But this is something that we talked about earlier when we introduced the ionic compound in chapter 2 and chapter 3 here. So all of the ionic compounds are solid at room temperature, and they have very high melting point, very high boiling point, and if they dissolve in water, the solution conducts electricity. And now, the formation of the ions, now using this particular slide there, using sodium and chlorine as an example, well, there is a process where the electron being transferred. So you start with 11 protons and 11 electrons on sodium, and you start with 17 protons and 17 electrons on the chlorine there. Chlorine being the non-metal, is going to take the electron from sodium. So in this case, and sodium is going to lose one electron, and the chlorine is going to gain that one electron. So there's a transfer of electron from sodium to chlorine. The result of that is the formation of what we call the NaCl, sodium chloride crystal. Now, NaCl, we don't use the term to describe this formula as a molecule. And there's no NaCl unit per se in the compound of sodium chloride. And there's 1-to-1 ratio of sodium ion and chloride ion. Okay. If you put them in water, and these two ions will separate from each other, and they become positively charged ion, negatively charged ion, they become free ions, they can move freely. That's why the solution conducts electricity. Sugar, on the other hand, if you dissolve sugar in water, carbon 6, hydrogen 12, oxygen 6, they will cluster together. They do not separate from one another. They do not bear charge. As a result, the sugar solution, water sugar dissolved in water, that solution, if you don't have anything else, that solution will not conduct electricity. Okay, so this is the ion compound formation. Now, what really happens here is that sodium has one well, we were just talking about that, valence electron. Sodium group 1A, so sodium has one valence electron. Chlorine group 7A, 7 valence electron. Okay, so in this case, each atom, it has a tendency to get a noble gas electron configuration. Now, sodium is number 11. The noble gas element in front of him is neon number 10. Okay. Now, if sodium atom loses one electron, that will go back to the electron configuration of neon. Okay. Now, chlorine number 17. The closest noble gas elements to it is number 18, argon. So, if chlorine can get one more electron, then chloride ion will have the same electron configuration as argon. So chloride ion will be happy, sodium ion will be happy. While sodium, by donating the atoms of sodium, by donating that electron, they go back to the noble gas electron configuration, the noble gas elements in the previous period. So they're going backward by losing electron. While chlorine, by gaining electron, they get to the electron configuration of the noble gas elements in the same period. So what happens here is that the formation of the sodium ion, chloride ion, these two ions each will have a noble gas electron configuration with 8 valence electrons all around. Okay, so this is the process of formation of the ionic compound there. But for the molecular compounds, though, molecular compounds can exist in gas, liquid, and solid state, whenever around the room temperature there. And they have relatively low melting point, boiling point. Well, that's a relative term comparing to the ionic compounds there. Now, if you dissolve molecular compounds in water, well, their solution do not conduct electricity. We call them non-electrolytes. And they are composed of non-metals only. There's no metal involved in there. So every time you have a metal, main group metal elements or transition metal elements, you have an ionic compound. But when you're talking about molecular compounds, they are always composed of non-metal elements. So that's the difference between the two. Well, the question is, why are the properties of these two different types of compounds so different? Well, it's the nature of the chemical bond. Whatever is in that each type of the compound in terms of chemical bonding. Ionic compound, transfer of electrons. So the key word is transfer. There is a gain of electrons, there is a loss of electrons. Okay. And in the covalently bounded molecules, there are molecular compounds. Electrons are shared between non-metallic elements. There are non-metal elements there. So sharing and transferring, that's the key difference there. Okay. And when you're looking at a diagram that we sometimes draw to represent a particular type of compound there, this would be an ionic compound. You do have a positive charge, a positively charged ion, and you do have a cation, you do have an anion in there. Okay? So when you see drawings like this would be a representation for ionic compound. However, for molecular compound, well, you actually have 2 or more atoms clustered together to form one unit. Well, this would be a molecular compound. So if you look